Alright guys, best notes of the year, Ice Ice Baby. I might just listen to this song and repeat the whole video. Just kidding. Okay, hopefully if you're watching this video, you already know these things. You can write K expressions or the equilibrium expressions based off a graph or based off a balanced equation. You can look at a graph and calculate K and tell me what's favored. So if K is bigger than 1, products are favored. If K is less than 1, reactants are favored. You can solve for K when you have the reactant and product concentrations at equilibrium. You can plug those into your K expression and solve. Or you can solve for K if you have partial pressures. That's just Kp. You hopefully can also solve for Q if I give you the initial reactant and product concentration or pressures, or I give you not the initial but at a certain point in time the pressures or concentrations of reactants and products. You can also use Q for that. And then hopefully you can tell me which way a reaction will shift. If I have Q and I have K, I can figure out if Q is less than K, the reaction will go to the right. If Q is bigger than K, the reaction will go to the left. And if they're equal, we are already at equilibrium. So the big question then is, what do we do if we don't have the equilibrium concentration or pressures? They're not given to us. Maybe they give us only initial conditions but not equilibrium. How am I supposed to figure any of these problems out? Well, if that is the case, then we're going to do a little... Do you like that timing? All right, we're going to do a little ice. Well, what is ice? Ice is just a strategy that we're going to use. It's a problem-solving strategy to figure out equilibrium concentrations or pressures if I have a balanced equation and I have initial conditions. In order to do this, we also need the K value, though. All right, so let's just jump right in. So here's a typical problem. You start out with only H2O gas in a rigid container at 25 degrees Celsius. That just basically tells us the temperature is not changing, so we can kind of ignore that. And the initial partial pressure is recorded to be 0.784 atm. What are the partial pressures of each species when the system reaches equilibrium? And they give us the Kp because we're looking at pressures, so we have a Kp expression. So step 1 is to make an ice chart. So we take ICE underneath the balanced equation. I stands for initial, C stands for change, and E stands for equilibrium. The first thing we're going to do is plug into the initial. So you can plug in concentration or pressures. In this case, since it's all about pressure, we're going to just stick with pressure. So they told me initially the water, the H2O vapor, has a pressure of 0.784 atm. They did not mention the other two, the products, that there's no starting amount. So we're just going to leave those guys as 0 to begin, because this is initially before the reaction has actually happened. All right, C stands for change, and this is kind of similar to our BCA table. But for the sake of these problems, we always are going to go towards the 0, right? So we have 0 here, so that means we're going to start by going in the forward direction. Even though this is equilibrium, we've got to start making products. So we moved. What that means is we are going to use up, so minus 2x, so 2 times a certain amount of the water. And then the products we're going to make plus 2x of the hydrogen and plus 1x of the oxygen. So whatever direction you're moving, in this case, we're moving the forward direction. We get positives, and then we're using up some of the reactant, so minus 2x. E stands for equilibrium, so I'm literally going to take the I plus whatever is in the C box, or in some cases minus, right, if there's a subtraction sign. So 0.784 minus 2x, this minus this, 0 plus 2x gives me 2x, 0 plus x gives me x. The important thing is this line here. This is going to help us find the pressures at equilibrium. So these are what we will plug into the K expression. The equilibrium line, remember the K expression is just for equilibrium, so the equilibrium line is what's helpful for the K excuse me, for plugging into the K expression. So next, I have my K expression. Remember, it's products. So this hydrogen, H2 squared, times oxygen, divided by the water squared because of that 2. So there's my Kp expression. These P's are telling me that we're using partial pressures. Notice we're using parentheses instead of brackets for partial pressures. Brackets are for concentration, parentheses and that capital P are for the partial pressures. Next, I'm going to take that E line of my ice table and plug in. So notice these guys here all came from the E in the ice table. So we're just plugging those in even though, table. Plugging those in and eventually we will solve for X. Alright, so we have this K expression. In the problem, remember they told us what Kp was. So Kp was 2.0 times 10 to the negative 42nd. So I'm going to plug that in. So 2.0 times 10 to the negative 42nd equals 2x squared times x divided by 0.784 minus 2x squared. I have a little trick. When Kp or Kq is smaller than 1.0 times 10 to the negative 5th, you are allowed to ignore any minus x's or plus x's. Because basically what's happening is when we solve for x, it's going to be so small that basically by taking 0.784 minus something that's like 2 times 0.0000001, it's not really going to make a difference. And then you start getting into sig figs. The reality is we started with 0.784. We're using up such a tiny bit of it, it's not going to actually make a difference. And that makes our algebra easier, okay? So I'm going to, on your paper, what you'll do is you'll set it up properly, but you'll write something like this. You'll put an X through it so I can still see it's there and say omit because K is small. And we'll actually do a check later to make sure that it's small enough. All right, so I rewrote now without that minus 2x. So notice I didn't omit all of the x's. I just omitted the subtracted x, and I actually simplified the top. So I get 2.0 times 10 to the negative 42nd. 2x squared times x gives me 4x to the third. And then I got rid of that minus 2x, so it's just 0.784 squared on the bottom. Squared, I get 0.615. And then what I'm going to do is, let's put this guy over 1, right? Dividing that by 1 or putting it in a fraction over 1 doesn't actually change anything. But now I can see that I can easily crisscross multiply. So I will get, when I take 2.0 times 10 to the negative 42nd times 0.615, I get 1.22 times 10 to the negative 42nd. And 4x to the third times 1 is just 4x to the third. Next, I'm going to divide both sides by 4. So that gives me 3.08 times 10 to the negative 42nd equals, my 4's cancel, x cubed. And then I'm going to take the cubed root of both sides, and that should hopefully then give me x equals 6.7 times 10 to the negative 15th. All right, next step is we have those E lines of the equilibrium, but when in the ice table they were written as with x's. So now that we know what x is, we're going to plug it in and solve for our equilibrium concentrations or our equilibrium pressures. So we just said x was equal to 6.7 times 10 to the negative 15th. So what I'm going to do now is plug in. These are the E lines. So this was the E, this was the equilibrium, and this was the equilibrium for our ice tables. So all we're going to do is plug in that 6.7 times 10 to the negative 15th for x. So I get 0.784 minus 2 times my x value. And I calculated this before. Look at that, 0.784. Remember when we solved for x, we omitted this because we said it was so small it wouldn't make a difference? This is our proof that it didn't actually really make a difference. Okay, Then 2 times our x value will give me 1.35 times 10 to the negative 14th. And we're in pressure, so atmospheres, ATM. And just x, that's the easiest one. So there's our equilibrium pressures. We have our answers here. I should be able to plug in to my K expression, right, and get the same answer of K that was given to me in the problem. So you should always be able to know if your answer is correct because it should match the given K in the problem. Minus 2x is called the 5% rule. So what we assumed is that minus 2x wouldn't make a major impact because K was smaller than 1.0 times 10 to the negative 5th. The way we can confirm this is we want to make sure that what was omitted, 2x, is less than 5% smaller than what we started with. So here's what we do. We take the 2x, whatever we omitted, divided by the starting pressure or concentration, which we omitted from, which was 0.784. So basically, I am assuming, or I want to check, that what I omitted is less than 5% the size of what I started with. So luckily, we know what x is. We solved for that. So I plug that in. And then we'll times it by 100 to make it a nice percent. And so what I get is 1.72 times 10 to the negative 12th percent. That is way less than 5%, so the omit is valid by the 5% rule. So this work needs to be done off to the side or at the end of a problem to prove if you're going to omit something, I will be looking for the 5% rule to be proven somewhere either right next to where you omitted or at the end of the problem. Okay? And then you can always check your answer as kind of a step 5. So for example, on that last slide, all right, another ice problem for you. Find the equilibrium concentrations of all the species if 0.194 moles of COCl2 is allowed to come to equilibrium in a 5.8 liter container at 25 Celsius, and they give me Kc. Step 1 is find the concentration in moles divided by liters, or molarity. So in our ice table, you are only allowed to plug in concentration for molarity or atmospheres, ATM, the partial pressures. So if they don't give you molarity or partial pressures, you have to find concentration. So I took moles divided by the volume to get my starting concentration. This is my ice, my I for ice, initial concentration. So now we can set up our ice table, ICE, initial change equilibrium, under the balanced equation. This is my starting molarity that we just found, and no products. So that means my reaction is going to move to the right. If my reaction moves to the right, it means I'm using up and I'm making. So that's where the minuses and the pluses come from. And notice this one's nice and easy. The stoich is 1 to 1 to 1. So that's why the x's are just 1, 1, or 1x, 1x, and 1x. Take my I minus my x, my I plus my x, my I plus my x. That's how we get our equilibrium boxes. And remember, the equilibrium is what goes in the K expression. So here's my K, my products divided by my reactants. They're all 1 to 1 to 1. And so then I plugged in the E lines to set it equal to Kc. When we first read the problem, they told me what Kc was. That was given to us, and it's very, very small, to the negative 38th. So I can omit, because K is small, that minus x. Notice I'm not omitting these x's. Those are important, but when I'm taking a very, very small number and subtracting it, it's not going to really make a difference from whatever I'm subtracting from. So only adding or subtracting x's can be omitted. X's or 2x's or 3x's, multiplied x's, so to speak, cannot be omitted. So we omit that. So now I've rewritten, I just have x squared on the top, x times x, and just 3.3 times 10 to the negative second on the bottom. All right, So I'm going to do some algebra. I'm going to crisscross multiply. So taking 7.27 times 10 to the negative 38th times 3.3 times 10 to the negative 2 gives me 2.40 times 10 to the negative 39th, and that's equal to x squared times the 1. To get x by itself, I have to take the square root of both sides, so that will leave me with x equals 4.9 times 10 to the negative 20th. Let's plug that in. 3.3 times 10 to the negative 2 minus 4.9 times 10 to the negative 20th gives me 3.3 times 10 to the negative 2 molar. Doesn't really change because to the negative 20th is so small. That equals x. Those are my favorite. 4.9 times 10 to the negative 20th molar equals 4.9 times 10 to the negative 20th molar. Those are my final answers. So let's check the 5% rule. We omitted x from the starting concentration, which was 3.3 times 10 to the negative second, and we want to times that by 100. So x was 4.9 times 10 to the negative 20th. That was when we solved. Divided by 3.3 times 10 to the negative 2 times 100. That gives us 1.4 times 10 to the negative 16th percent, which is way less than 5%. So omit was valid. So that's my little check off to the side to make sure that I don't have to go back and do the quadratic formula. We omitted x because it was so small, it made my math a lot easier. All right, so here are the general steps. Write the balanced equation, and then you need to get everything into moles if necessary. If they don't, first in moles, you have to get everything to molarity. So sometimes they're going to give you some weird stuff and make you find moles so that you can ultimately find molarity or atmospheres. Okay. Once you have your balanced equation, you can set up your equilibrium expression. That's your K equals the products divided by the reactants. And you can set up your ICE table, I, C, E, and fill in your initial concentrations or pressures. Calculate the change, so this is your minus x's or your plus 2x's based off the problem and the coefficients, and then you'll solve for E. Remember, I plus C equals E. And then once we have E, we can substitute those little algebra statements into the K expression and solve for X. Once we have X, once we have that X, we plug it back into the E line, and that gives us the equilibrium concentration or the equilibrium pressure. Okay, some tricks. Look for when K is small, like it has to be smaller than times 10 to the negative fifth. X can usually be negligible, so you can do the 5% rule, but you have to prove and check that 5% rule was valid by plugging in whatever you omitted, divide it by the initial concentration, and if it's less than 5%, then you're good. Say like K is big, it's bigger than times 10 to the negative fifth, you probably will have to do the quadratic formula, but usually look for a perfect square. That's way easier to solve. Take the square root of both sides. The AP exam has never made kids do the quadratic formula. So usually it's K is small enough so you can omit, or it's a perfect square to solve for X. Lastly, one thing we're going to look at real quick, if none of the initial concentrations are zero, because remember the reaction always proceeds towards the zeros, but what if everything has a starting amount, which is pretty common in nature, right? Like maybe we're making carbon dioxide. Well, we already know there's carbon dioxide in the atmosphere, right? Not everything starts at zero. We have to first find Q. So we plug in the initial conditions and see which direction the reaction will shift. And that will change our plus x's and our minus x's, right, based off the direction of the reaction. So let me just show you one real quick. We're going to fly through it where you have to solve for Q first. So here's the example. We have hydrogen iodide, and they give us the K expression. and they tell me a starting amount of HI, a starting amount of H2, and a starting amount of I2. Well, this is equilibrium, so I don't know if the reaction is going to go this way or this way, because normally the reaction goes towards where the zeros are, but they're all starting with a certain amount. So let's look at how we solve this. All right, I know this is overwhelming. I can't really cover parts up, so I just want you to follow with me. I plugged in the initial pressures, and instead of jumping right into the change, I calculated Q. So the Q expression is exactly the same as the K expression, product squared divided by the reactants, products over reactants. But the difference is, the reason it gets a Q instead of a K is based off what we plug in. So I'm going to plug in these initial numbers into my Q expression. And what I get is Q is equal to 5,000, or 5.0 times 10 to the negative third. In the problem, they told me K is 1 times 10 squared. This means that Q is bigger than K, which means the reaction is going to shift this way, to the left. So the reverse reaction is really what's happening right now. So what I did, if the reverse reaction is happening, it means we're going to make some H2 plus X, we're going to make some I2 plus X, and we're going to use up some HI minus 2X. I then did I plus C and got my E line, and now I'm ready to do everything else the same. I have my K expression. It's exactly the same as the Q expression, but the difference is we're only plugging in equilibrium, which is the E line. So I plug in those E lines, and then I know what K is, so I set it equal to that 1.0 times 10 squared. It's summer, so I don't really feel like showing you how to do all this math because it's a quadratic, so I just plugged it into my fancy calculator, and I got X is equal to 0.072 or 0.035. If you want to solve it out, go to town. That seems like a waste of time right now, but the whole point of this problem was for me to show you what to do if you have starting amounts of everything. Anyways, X can't be a negative number, so it has to be this 0.035. So I took my equilibrium expressions and I plugged in that X value to each and got my final pressures at equilibrium. So the only difference here was I had a starting amount of the product, so I could not assume the pluses and the minus signs. I had to solve for Q to figure out what we were making and what we were using up. Hope that is a good overview to ICE.